when you talk to it. Good morning. Welcome to Goddard Space Flight Center and next edition of our Comet Update for Thursday. This morning we would have opened up, as you saw, with the first real color image from the Hubble Space Telescope of the impacts, and that was the G fragment impact site. We'll roll that again later. Today we'll tell you more about that, as well as give you a look at comet fragments Q1 and 2, and that's 10 hours before impact and just after impact. And we'll bring you some news from comet observers from around the world, including looks at fragment R and a surprising report on fragment M, impact of fragment M, which had totally disappeared from view a couple of months ago. And we'll have more information on that and what's coming up later in the next few days following the presentations. Let me introduce a panel now. To my left, Dr. Hal Weaver, a scientist at the Space Telescope Science Institute and a leader of the team using Hubble's Wide Field Planetary Camera 2 and Faint Object Spectrograph to observe the structure and breakup of the comet. To his left, Dr. Rita Beebe, a planetologist of long standing at New Mexico State University and a member of the Wide Field Planetary Camera 2 team observing Jupiter's atmosphere. And back with us again today, Dr. Eugene Shoemaker, coming back for another day, a longtime comet watcher and co-discoverer of the comet Shoemaker-Levy 9 with the Lowell Observatory and the U.S. Geological Survey. To his left, Dr. Lucy McFadden, also back with us again today from the University of Maryland, University of California. And she's the coordinator of the Worldwide Comet Observing Campaign and a visiting professor at the University of Maryland. And to her left, David Levy, a co-discoverer of the comet, and he is author of some recently published books. And at this point, I'd like to turn this over to Gene Shoemaker.
Thanks, Don. We'll give just a little bit of an update on the status of the fragments. One that's of particular interest to me is that Keck reported seeing the impact of fragment M, which had actually disappeared from view for a while. And there's been great debate as to what do these things actually dissipate, or is there really something, is there really a piece there that simply stopped being active? And I think both Hal and I have been on the side that yes, there's really something there, it's just sort of turned off. And so both of us are very pleased with that report. And then Hal's going to give our last look at two pieces of fragment Q1 and Q2, what was happening to them as we were watching the comet going in. Hal?
That's right. We might call this show right now Watch This Comet Die, because the Hubble most of this week has spent its time focused on Jupiter, watching the spectacular display that you've heard about all this week. But we can't forget about our kamikaze comet. Of course, that's the source of all the activity we're seeing, and we really can't understand what's happening on Jupiter until we understand what it is that went plowing into Jupiter. And as Don was saying earlier, the Hubble actually swung off of Jupiter and observed the very interesting Q region in the comet. This is one of the brighter regions, only 10 hours prior to its plunge into Jupiter. Now, I thought before I showed you the pictures of the final pictures of Q that I would step back and just give you a status report on the comet, give you sort of a roadmap. If we can show the first picture. I think most of you recognize now we've been lettering these cometary nuclei from A through W. There are 21 pieces. And A was the first one to go in on Saturday. And we're now up to just in front of the S impact. And S is going to be going in about 3 hours from now, about 11 a.m. And you see a couple of pieces before S, you see the Q region. That has always been recognized as a very interesting region. But if we go to the next graphic, you'll see what is left. If we can dissolve to the next graphic. Okay, 16 of the pieces have gone in. We got 5 left to go. And Q, as I said, has always been recognized as one of the more interesting pieces of the comet. And if we can go to the next graphic showing the Q region, as we saw it in late March, you'll see why it was so interesting.
I think having a
Can we
technical
roll the next
difficulty.
graphic, please? We're waiting.
Could you roll the next graphic, please?
You can kind of make out here why Q is special. It's obviously not, okay, this is showing what's left. Most of the comet is gone. Most of it has died away. And unfortunately, we only have these few pieces left for those of us who like comets. Now, if you can go on to the next picture. And this is how Q appeared to the left. This is how Q appeared in late March. There was actually 4 pieces in the field at that point, Q1, Q2, and then down below those are the so-called P region. And Q, you can see, is a double object. And that's what made it so interesting. Most of the fragments in the comet had remained stable for about 2 years, not showing any evidence of breakup. But Q, from the time that we started observing it, they had these 2 bodies close to each other, indicating that there was a fragmentation of Q subsequent to the breakup of the original body. And based on that, some of us thought that maybe Q was a good candidate for breaking up further as it came into Jupiter. That's why we wanted to take the last look, because the amount of energy that's that goes into Jupiter's atmosphere and causes these explosions depends on how much mass. And if this thing is going to be breaking up into small pieces before it goes into Jupiter, you get much less bang. So yesterday morning, we took the picture to the right, which shows how dramatically stretched out the comet is getting just before going into Jupiter. It stretches out along the direction, along the path of its motion into Jupiter. And you see that Q1 and Q2, the Comet, which is the dust around the comet, is getting stretched out along the direction of motion, but the fragments are hanging in there. Just 10 hours prior to the impact, they're still hanging in there, indicating that there should be a substantial splash when it hits Jupiter. Now, at that point, I think we're ready to turn it over to Rita and find out exactly what happened as the Q impacts went into Jupiter.
I know you're all waiting for the triple whammy. Actually, from what he's just told you, it's a quadruple whammy, because we have Q1, Q2, and then we have RNS going in. The planet rotates once every 10 hours. Q2 and Q1 were scheduled to arrive so that they should have impacted about 12 degrees apart. And then almost 10 hours later, R comes in, and almost 10 hours later, S comes in. So that this impact site will have only 10 hours to recover from site to site to site. Could I have my first graphic, please? Could I have the next one, please? Could I have the next one, please?
Next graphic, please.
Next graphic, please.
Okay, they don't have another.
Okay. We'll start with the one that was displayed when we first came in. That one showed the G impact site about 1 hour and 45 minutes after that the G had impacted. D had impacted considerably early, but D was quite a small one. It's just a small spot sitting off to the side. Now, could I have the previous graphic, and we'll see the same region 61 hours later. Could we go back to the other color graphic, please? So here you see the development site. D is the impact site in the upper portion, and L has arrived in the interim, and it's below the two white spots off to the left of the screen. So here we see how these bodies have evolved over, in the case of D, 61 hours, and in the case of L, 39 hours. Off on the limb of the planet, up at the top of the screen, we see Q, the impact Q just coming around, so that from this point of view you can see that Q has landed. Now, Q2 was scheduled to arrive so that it would have impacted 12 degrees into the field of view here. If it arrived, according to Paul Chodas's last computed time arrival, it should be the tiny little brown spot that you can scarcely see. If you look across from the Q impact site toward the G impact site, there's a small brown comma in there, which is almost invisible. Now that's either Q2 or that's a Qlet. Q broke up. Q2 is a younger fragment than Q1. So it's quite possible that there are other fragments. We have only one orbit of data, and we got this down at 2 o'clock this morning, so we have been busily setting this up for you. And we haven't had any chance to check. So one thing we can say about this feature is that this is the smallest impact site we have seen yet. And certainly when you consider that, the fact that it is brown is interesting. Now, can I have the other graphic, please?
Describe which one it is you're looking for.
Okay, this one.
That's it.
Okay, now this one is taken at about the same time in the methane filter. So that every place on this that is dark because the sunlight is coming in and the methane gas is absorbing it before it can get back out. Now, look for our little friend in that. You see the Q site on the edge of the planet there. That may be a complex of Q2 and Q1, or that may be Q1. And then down along the track, you see a tiny white spot. Now, in the insert, you see a grossly filtered view, and you see the pattern of the evolving G site, and you see the Q site at the top, and in between you see a little white spot. Now, this is much, much fainter than the D spot was when it was young. It was quite easy to see it in methane light. So this definitely is our baby of the whole family. And what's interesting is that in the images that I put together to make the color view for you, it had the same color dependence as any of the big spots. It too is dark in all of those colors. So whether it's Q2 or not is really not that significant. What's really significant is that this tiny little one went in, and it's behaving in the same, it has the same color behavior. Enough material came up to get high enough above the clouds to reflect and be white, and still in all the other colors, it's dark. So that we now are sort of getting a lever on this, and this may help us to argue whether this material is really coming from a comet or not. Now, we have a problem. About the 17th of May, Hal took an image that he had, and he assumed that the brightness of the comet was equivalent to the mass. And from that, he computed the energies of impact. And if you set the impact energy of A equal to 1, the impact energy of D was equal to 1. And the impact energy of G was equal to 24. Now, he had predicted that the impact energy of Q would be 25, and the impact of Q1 would be 25, and the impact of Q2 would be 10. L was 15, so L is in line, but if this is Q2, it's really out of line. But I was astounded when I saw the impact of A, because I was waiting for G, which was going to give me a reasonable impact. So here we're finding out that the assumption he made is proving not to be true. Now, it was the only one he could make at that time to get some sort of a handle on it. We did a lot of our scheduling around it. But at that time, Hal warned us that there might be a different problem involved here as well. It turns out that A, F, and Q2 are not on the same line as all of the other comet hits. So the result is that they have been ejected in the breakup. I'm sorry, it's D, F, and Q2. They have been ejected in the breakup, and Howell warned us that they might not be like the others. They might not be as consolidated. They might be composed of a spray of particles that had been ejected. And so far, Hal has got a smile on his face because all of the ones that were out of line are, if this is Q2, he's got a straight run here, batting 400 on his small particles that are out of line.
I'd say he's batting 1,000, wouldn't you, Rita? we haven't gotten them all yet, but that really, just to encapsulate what you said, what that's really supporting is that the guys that are in line, which seem to be initial fragments from the breakup of the comet when it got closest to Jupiter, are more or less compact objects and are behaving like we would expect from the photometry, whereas these guys that are off the line are more likely swarms. And so we can get greatly fooled by the brightness then as to what's really there.
But this also means that we have two kinds of probes.
Yep. Isn't that neat?
Yes.
That's great. Okay. Let's go on here now to David Levy for an update on what the amateurs are seeing.
Yeah, there's quite a bit to say. There are a lot of continuing reports of very large dark spots visible at the impact sites, particularly K, L, and G parading across the disk. Report from England saying that they are more spectacular than ever, very large and dark, and reports from everywhere indicating that they are about as big as the Great Red Spot. They are as dense as a satellite shadow. And for those of us who have have some experience looking at Jupiter, as a satellite parades across Jupiter's disk, it transits the disk, and you can see a very dark shadow cross Jupiter. And this takes a couple of hours, especially the moon Io transits. And these are benchmarks. When you see a satellite shadow, it usually is the easiest thing to see on the planet. And here we have dark spots that are not satellite shadows. They are every bit as easy to see as the satellite shadows, but they appear to be as large as the Great Red Spot. At least the large impact sites are as large as the Great Red Spot. This means that these are the most obvious features ever seen on the planet Jupiter. This also means that just about anybody can go out and look at these. And as I mentioned yesterday, I recommend that people that don't have a lot of experience looking at Jupiter should still not pass up this opportunity to get acquainted with this beautiful planet. Go to your planetarium if they're having a star party or amateur astronomy club and get someone to show you this beautiful, beautiful sight. And if I can stop going to these dinners and stuff that we're having, I'd love to see this myself. But whenever it clears up in Washington, I'm told that I have to eat something.
But wait until you get to Tucson. The seeing is much better in Tucson.
Yeah, I know. I can't wait to do that. There is some interesting news, though, for what's in the future. Tonight, the final two fragments, which is really kind of sad to say, but the final two fragments are going in, and V and W. V comes in around 12:15 or so Eastern Daylight Time, which means that for us, Jupiter is going to be set, and we won't be able to see anything on the east coast of the United States. For people on the west coast, though, Jupiter will be just dandy, just sitting there, beautiful evening sky. There is, and I want to caution that this is very unlikely, but if there is any chance for visual observers, experienced visual observers, to see the flashes of the impacts, either the incoming meteor as the fragment starts going in to the stratosphere, or the explosive plume that we call the fireball that comes afterwards and lasts quite a bit longer. The best chances come tonight with fragments V and much later W. W will be easiest to see for observers in California. Jupiter will be low there, but Hawaii, the South Pacific, and observers in Australia and New Zealand should have a good chance. W is a pretty good fragment. It's pretty fair size. It's a nice one to end our party with, and also is the one that is hitting closest, I think, to the limb of Jupiter, to the edge of Jupiter. So what's happening tonight is we can go out and look at the dark spots, and also, if we're in the right position, to try to see if we can see any flashes indicating the final impacts. Okay, Gene?
Thanks, David. Lucy, can you bring us up to date on the latest impacts? Fragment R impacted about several hours ago. How are we standing?
Sure, I'll try to. There's a lot going on, so it's a challenge to keep up with what's happening. Fragment R impacted several hours ago, and we have this report from David Schleicher at the Lowell Observatory in Flagstaff, Arizona. Accompanying this, I'll keep talking until we get the image up, we have also confirmations from McDonald Observatory. Oh, here, let's listen to Schleicher's report.
It appears as if we are detecting a plume from the impact of R. This is using methane filter 8,900 angstroms. We're somewhat surprised at being able to see it at all, because I don't recall there being that many detections of plumes in the visible. Most of them have been in the infrared so far. It may mean that it was a bigger piece than some people have been anticipating.
Well, I think Dave was suffering from a astronomer's fatigue because there have been a number of reports. McDonald Observatory was looking in the same methane band, and they did see a bright emission in that spectral region. The Keck Observatory also reported, Imke de Pater from UCLA and her team reported seeing a truly remarkable flash from the impact of R that lasted for about 20 seconds, and then the plume, the hot rising gases, appeared 8 minutes later over the limb and brightened and then faded over a period of about 8 minutes. Now we have a report from the Galileo spacecraft, and as you recall, this is really significant return because Galileo is looking directly down on the impact sites, and they actually can see when the initial explosion occurs. We have Terry Martin reporting.
Today, we were pleasantly surprised to pick up event L, which was originally not expected to be captured because of the timing relative to the predictions of impact, but the actual impact occurred later, and we picked it up. And this one is actually brighter than H by almost a factor of 2. It's more like 5 to 6% the brightness of Jupiter, and it takes 35 seconds or so for the light to die back down again. So we think that we are seeing the actual meteor flash, the transition of the fragment through the atmosphere and the very hot emission from that, but over a very small streak of light across Jupiter. And this is of short duration and precedes the plumes and the fireballs that are being seen from other observatories.
Let's hold that up if we can. Can we bring that back? Because I need to address the inset in there, if possible. What you are seeing is a tracing of intensity as a function of time. And if you can recall the inset, and we'll review it again later, time proceeds along the bottom axis, or the horizontal axis, and the flash is represented by a quick increase in intensity, and then it decays as time goes on. Then let's see, we're sort of working backwards in the alphabet of impacts now, with some reports that are coming in. We have the European Southern Observatory showing the K impact fireball and showing the plume, and I think we'll just put that up briefly. Okay, yes, here we have the residual from the G impact and the quite prominent H impact. Now I would say all observatories are reporting that there's detectors, that they're overexposing their images. even when the first reports came in and reported overexposing or saturation of their detectors, I'm sure everybody reduced their exposure times, yet they're continuing to be overexposed. So again, we just continue to be surprised at how bright these impacts are. We have a movie from the Sac Peak Observatory, which is a solar observatory in New Mexico. And we will run that. I haven't seen this. This is of the G fragment impact, and it's a time series. I'm sorry, Sacramento Peak. I used the abbreviation. It's the National Solar Observatory. So we can see Jupiter rotating with time. And these data will be analyzed in terms of changes in the brightness and any spatial variation which can be determined. And we will, of course, correlate these results in the infrared with the visible and ultraviolet images that are acquired from the other ground-based observatories and the Hubble Space Telescope. Now we have our first report from another Earth-orbiting satellite, the Extreme Ultraviolet Explorer. And we have a video of that and a voice report first.
Has not really changed that much yet, which may or may not be a surprise, since it'll take a little while for this stuff to reach the torus. But one thing we have seen is that if we look at Jupiter alone in the extreme ultraviolet, we actually see signs of helium emission during the impacts that we don't see before. The plumes did go up fairly high because we have to have thrown helium far up in the atmosphere to be able to see this, several hundred kilometers, in order to see this emission through all the hydrogen that absorbs at these wavelengths.
Okay, we're showing there, first of all, two things. One was a bright emission band from helium seen in Jupiter's atmosphere. And then they're also reporting about the torus around Io, the moon of Jupiter, which is a ring of charged particles. And they're reporting that they have not seen any changes in the density of charged particles around Io. So that's a preliminary negative result. And finally, we have images from Australia, from the Siding Spring Observatory, showing the C and G impacts. Oh, and it says, speak from my notes. Well, I'm not prepared to speak to this, but these are nice images, and I haven't done my homework. So I'm sorry, Australia, but these are the C and G impacts at different wavelengths, which my guess is looking at different levels into the atmosphere.
The first one looked like a methane band image, don't you think, Lucy?
Yeah, we've got 3 wavelengths. And I'm sorry, we're just going to have to pass on that one.
Okay, maybe this is the time for us to turn it back over to you, Don.
Okay, we'll have a question and answer, but first I want to make an important announcement on our schedule for tomorrow. That's a Friday briefing. Has been changed to 2 p.m. Eastern Time. We will not have an 8 o'clock in the morning briefing. This is to give the science team time to prepare the information and images on the 1-2 punch of Q&R. So we'll have that tomorrow at 2. And then as a preview for Saturday, we're going to also change the time to 11 o'clock a.m. Eastern Time. And on that one, we expect to have evidence for a sonic boom on Jupiter observed, and we'll also look at what is expected to be a dramatic plume from fragment W's impact, and look at changes we're already seeing on the impact sites. I'd like to open it up to Q&A from Goddard first. Please wait for the microphone. State your name and affiliation, please.
Paul Hoferston, USA Today. A question, I guess, for Gene and David. Weeks ago, there was so much emphasis put on we may see nothing, let's be cautious, and so on. I'm wondering if you can say now that that was a matter of maybe overestimating the resiliency of Jupiter, or was it underestimating the magnitude of these fragments, or some combination?
Gene, We're being criticized because it's been too good.
I would say the thing that caused the most uncertainty prior to the actual beginning of the impacts was the whole issue of how big are these fragments, how much stuff is there. Now we had two estimates, independent estimates, that suggested that the original precursor body was of order 10 kilometers across, and the biggest fragments might be in the ballpark of about 3 kilometers, or an upper bound that was given by Hal Weaver from earlier Hubble photometry was about 4 kilometers for the very biggest. That would have been, well, at that time it was Q that seemed to be the brightest. Now the issue was, are we really seeing the nuclei? Or maybe the nuclei are completely shrouded in dust. So Hal Weaver and his team that was trying to do this job tried to do the best job they could to subtract off the dust effect to see what's left, what's there in the middle. But you could argue that maybe that we weren't actually seeing anything else but dust, and that the nuclei could be much smaller.
We're defeated by physics.
Right. Basically, it's a very difficult observation. The other team that was proposing that these objects were big consisted of the dynamicist team at JPL, Paul Chodas and Don Yeomans and Zdenek Sekanina, and they said if they try to do their best fit to the actual orientation of the string of pearls, that they found a breakup of the comet initially about an hour and a half after it passed perigove. And they get from that, just that dynamical solution, they gave a size. You can get the size of the original object, because where the things go in the string of pearls depends on where they are relative to Jupiter at the time of breakup. So that's how you get the number. And it turns out their result agreed very nicely with the Weaver team, and we were very happy about that. But now there were other solutions. Jay Melosh and Jim Scotty, for example, said assume the breakup happens right at perigove, then the original parent body is much smaller. And so that's where some of the confusion was occurring. It turns out that solution is very sensitive to just exactly when the breakup occurs. Now the other thing that had come out very recently, particularly work by Willie Benz and Asfog, suggested that really the comet was just a pile of debris to begin with, and you could account for the string of 20 pearls quite nicely if you just smashed the whole thing. The whole thing just came apart, but then it gravitationally reaggregated by its own self-gravity into little clumps or knots. And actually there's a lot of power behind that argument. I think that we've got to address that argument, because I think that looks like a very strong argument. So the question was, are those clumps spread out, in which case they may appear brighter and there may not be as much mass, or are did the clumps get back together again? So something like G or H hitting Jupiter is really bound together by its own gravity and would come in, maybe get slightly separated as it enters the atmosphere, but effectively act like one projectile when it hits. Or would it be just going to be pulled out in a long string, and as Paul Weissman said, sort of hit Jupiter like a string of machine gun bullets, and that was the source of the idea of the Great Fizzle. It looks as though Jupiter is telling us, in my view at least, that you had pretty good clumps for the guys that are on the line. That's just what we were talking about today. So they're the ones that got back together and made pretty good clumps, and the ones that are off the line are the more diffuse swarms. That's been a guess, and it looks as though what we're really seeing on Jupiter supports that guess.
Bill Harwood, CBS, and just to follow up on that was part of the question I wanted to ask. The mechanism for the ones on the line and then the later breakoffs where you have these off the line, I'm interpreting what you just said, that it was all clumps to start with. Some got together and made big clumps, and some never managed to do that. Is that what you're saying? The mechanism of it. And the second question was, in the G impact site, where there was that sharply defined ring that we said we were going to look later and see if it was expanding. Has anybody looked, and do you know what that is yet?
Let's take the first part, and then I think I want to throw the second part to some others here. The first part is that some of the things that are off the line demonstrably split off from other clumps late in the history of the comet, because we essentially almost caught them in the act of separating with the images taken last July with Hubble. Q1 and Q2 are just starting to come apart, and P1 and P2 were actually not very far separated. So it's clear that those things began to separate even after the event, and those things that separated late, in part, seem to be the things that have drifted off and maybe mostly swarms.
Yeah, the Q fragment actually, there's evidence that fragment Q was starting to split up at the time of discovery of the comet, and that the date of around April 1st, 93 for breakup of fragment Q might
From Q making P, probably, at that time. Q and P being formed that way.
I was just going to say that I have a slight modification of what Gene was saying. My picture of what's going on for these fragments that are off the train is that in fact there still are single large bodies at the centers of each of those things. They're anomalously bright because they have more dust. The younger object, the younger the object is, the more dust it has. We see that even for the main fragments. The amount of small dust gets blown away eventually by the solar radiation pressure and is removed from the system. That makes the comet appear fainter because what you're observing for the most part is this dust. And if you have a younger object, if you compare the brightness of that object to something that's on the train, you're comparing them essentially at different times in their dust production. And so using the brightness is basically misleading you as an indicator of the size because there's more dust associated with these things off the train than the ones on the train. And, but I think that, for example, when you look at this interesting Q region, as Gene was mentioning, at the end of March, you actually see one of those small ones, the so-called P2, break up almost before our eyes into two separate condensations, essentially. I don't believe that could be explained by a swarm model.
It's hard to make.
It's hard to believe that. It's more naturally explained, it seems to me, as having a single object there that is now very fragile. I mean, we know these things are extremely fragile, and then it just broke off again. And that's why I was so interested in this Q region and watching it prior to its impact into Jupiter, thinking that, wow, this region, most of these fragments have already shown evidence that they're extremely weak, maybe even weaker than the others, and we might see these things coming apart. But up until 10 hours prior to impact, we didn't really see any evidence that Q1 and Q2 were splitting into, just a swarm.
Can we answer the question about the ring? Rita, could you?
I'd like to ask to defer that until tomorrow. Andrew Ingersoll is back at the Institute beavering away, trying to get this all put together for you. This is a part of his sonic boom scenario. So I think we'll just kind of hold that and let him work it out for you. Come on, there's a hint. If he's saying it's a sonic boom, you know it's got to be expanding.
It's Alan Marison from National Geographic Magazine. I guess this question's for Hal or Gene. You mentioned that fragment M had disappeared for a couple of weeks and then reappeared at impact, and you talked about the fact that this fragment turned on and turned off, and I wonder if you could describe what exactly that means and how that works.
Yeah, well, fragment M was only seen last year, okay? All of this year, nobody has seen M, and I think what happened there was that small dust basically got blown out of the system, leaving something that was a pretty small object, but still could be substantial. And the fact that you see evidence for the impact on Jupiter indicates to me that you still had something fairly substantial there, maybe on the order of 500 meters, something like that. Something that was below the detection limit of all the telescopes that are looking. For example, Hubble really wouldn't have been able to see something that's smaller than about 500 meters in size, even if it had no dust cloud around it. And so that's what we're seeing.
I should say that this is kind of a classical problem in observing comets. Many comets have been observed to essentially turn off and disappear. And we've always wondered, well, the two hypotheses were, did these just break up and dissipate, or did they simply shut down? They stopped being active, and therefore all you have is the bare nucleus, and it's too faint to see. And of course, I think Hal and I are very much on the same side of this issue, and that's why it's so delightful to see there really was something left when fragment N hit, because it's been gone for a long time, as Hal said. So the dust was gone, but there was still a body there, and it came on in and made an impact.
Question, third row.
Jim Reston for Esquire. Dr. Beebe, I'm still very confused about this water issue and the absence of the observation of water. Can you explain to us historically how astronomers in the past decades deduced that there was a band of water 50 to 100 kilometers deep into Jupiter's atmosphere? And that now when you're not seeing it obviously after all of these impacts, does that not suggest that there are four options here? One, that there is no water there, or secondly, that these things are exploding higher in the atmosphere and not going deep in, or that the impactors themselves are much smaller and therefore disintegrating before it reaches the 50 to 100 kilometer range, or lastly, that the black clouds are masking the material that is ejected, the water that may be ejected, and that the black clouds is cometary material. Which of those theories are we now?
I would say yes to the first three.
Okay, would you take it first how it was deduced before we had this experience?
Right. Don't blame the astronomers for this. Blame the chemists. Basically, if you assume that Jupiter was made out of the same thing that the sun was, and you do the chemistry, you realize that when you're going into the planet, when you reach a certain temperature, the ammonia ice will freeze out. And if you go below that, the ammonia ice will be gaseous. But as you continue down doing your equilibrium chemistry study, your balanced chemistry studies, you get to another layer where if there is hydrogen disulfide and ammonia there, they will combine and make a new kind of ice. And finally, as you go deeper and deeper into this planet that actually sends up 165% more energy than it absorbs from the sun, as you get down to those deeper temperatures, you finally get down there to where the temperature is about 0 degrees centigrade, and then you're going to have water, if there's any oxygen, because you've got hydrogen all the way through. Now, an obvious reason that we are not seeing this water is we didn't get down to it. And that's an easy one. But we then must look very carefully at all the spectra, identify all of the molecules, and try to get a self-consistent idea. And again, the chemists are going to come back and take over in the final analysis and tell us whether we're right. That's one of the very nice things about studying planetary science. We have enough different types of data that the astronomer goes out and gets it, and then the chemist and the meteorologist and everybody else tells us we're wrong and starts working on new models that improve it. So at this point in time, I tend to favor that we didn't reach the water level. But that water level is sort of a nebulous little thing. It ought to be there, but we really have never got a good sounding of it.
So just to encapsulate, is the historical view that there is a band of water 50 to 100
yes, there
kilometers, is that in jeopardy, that theory?
No, I don't think so. Unless when we've worked this out, we decide that they had to penetrate that deep. Then we'll have to raise that question. And if that's the case, then in December of '95, the Galileo probe goes in, and we get another crack at answering it.
Miles, and we'll come back to this side.
Miles O'Brien with CNN, and this would be for anybody who wants to take it. There's a report out of Australia this morning that observers there actually saw a flash in the ring of Jupiter. Question is, are you surprised that we haven't seen more of these observations before? And what did you hope to learn from the flash sightings indirectly in the first place?
Well, one should remember, seeing the ring of Jupiter is a bit of a feat in itself. It was, of course, discovered with Voyager 1, and only later was it actually seen from telescopes on the ground. Mostly you need a pretty big telescope, and the best trick is to look in an ammonia band, a methane band, so that you can reduce the light of Jupiter, but where the ring might be bright. That was being observed, I should say, at Palomar Observatory with a 200-inch telescope. The Anglo-Australian telescope is another good one to do this experiment, but it's difficult. What one really hopes to see, since the ring is in close, however it's fairly faint, the ring is in close, if you can capture the flash of the initial entry meteor, that was one way we could, by observations on the ground, determine the actual moment of entry into the atmosphere. Those first few seconds as the meteor is just plunging in the upper atmosphere, we're hoping to actually get a timing on that. And of course, it gets very bright as it approaches the ammonia clouds. So that times the actual impact for us, and that's an important thing to do. It's a delight we heard this morning that they're actually seeing those flashes now and picking them up. I think that's very important.
Wasn't just the ring that people thought you might see flashes in. It was also some of the satellites, and I might be mistaken, but I don't think I've heard many reports of flashes being observable in the satellites.
Right. I can speak to that, Miles. I have 4 negative reports of the absence of flashes observed as reflected off of the satellites of Jupiter. So the people have looked for. Everyone all right?
Was that us?
That's 2 hours early.
Good. People have looked for evidence of flashes off of the Galilean satellites. The reflection from the flash as it impacts Jupiter, they have reported not seeing that. So that has not happened. And I'd like to talk to you later about seeing flashes off the rings, because they were looking for that, and you're ahead of reading the information. No. Oh, surprise.
Difficult observations. The best candidate was K, because Europa was in shadow. Right. Those observations were going to be made mostly in Australia. Could have been made in Hawaii. That's the region. Yeah. And I haven't heard...
They were made, and they reported negative, not seeing anything.
There is one probable observation of a flash from Israel. Of a flash reflected off
Europa?
One of the satellites. It is a 0.06 magnitude, 600ths of a magnitude
increase in brightness.
Yeah, it's listed as a probable, though, not a definite.
Rita, you had something you wanted to add to this.
A second reason for wanting to see the fireball is that you know how far the ring is from the surface of Jupiter, and if you could measure the increase of brightness off of that ring surface, and you have an idea of the particle density in that ring from the Voyager data, how thick the stuff is, then you would have a measure of the fireball itself. We haven't been seeing the fireball. And had you gotten a sequence of these, even though you didn't understand the ring, the difference in brightness would give you this relative strengths of the fireballs.
When Rita says fireball now, she's meaning what's traditionally used as fireball for a very bright meteor.
That's right.
Rather than the fireball we've been using it here in this group as something formed deep in the atmosphere forming the plume. I just wanted to clarify that.
Yes, this would be the initial flash.
Initial flash.
Which would be very closely related to the amount of energy that was going in. It hasn't really even interacted with the atmosphere yet. So it would be very fascinating to get a whole series of these flashes and then just, oh, well, that one had the most energy. And
right. Well, Galileo is doing that. The photopolarimeter radiometer on Galileo will have that information.
We're going to have time for about one more question here, and then we have to go to headquarters. And we'll have more time after the satellite goes.
David Chandler from the Boston Globe for Dr. Beebe. 2 questions. On the latest color image of the G impact site, how do you interpret that apparent sort of brownish color that we're seeing there? Or can we learn anything from that coloring? And secondly, comparing the initial photos of the G impact site and the most recent ones, what can you say about the evolution of that impact site?
well, first of all, this large feature we're seeing has to be high in the atmosphere, because looking at the image in different colors, you can literally see the east-west cloud patterns to the north of it just pass right through this structure. I mean, this was an Olympic 10 dive when it went in. It didn't splash the atmosphere. The atmosphere underneath looks very undisturbed. Just passed right on through. And what came back out must have come right back out the chimney that the ingoing particle developed. So what you see now is you see this huge umbrella of material above the site. Now, the reason I'm on this team is that I wanted to see a bubble come up out of that site and interact with the winds, and I would then understand how much energy it had taken for all the storms I've been watching for the last 25 years. But so far my bubble hasn't come up, and my bubble may be under that brown material, but if that brown material were down in the ammonia cloud deck, it would be stringing out. It would be headed it would be headed east along the north side of the spot, and it would be headed west along the south side of the spot. So you just see the thing starting to run out as a banded streak. But we don't see that, so that it's still decoupled from the tropospheric winds. And we expect those winds to drop off with height in the atmosphere. When you get up to a certain point, you wouldn't expect it to be sheared out. So that's another limiting piece of observation that says this stuff is definitely high. To me, it's probably twofold. It's probably particle formation, which really obscures things, and those particles are dark.
We'll take questions from headquarters now. Please state your name and affiliation.
This is Dick Kerr from Science Magazine. Have there been any attempted observations of the impact of fragment J, and if so, what were the results?
I don't recall hearing anything. Anyone else?
That was one of the other missing nuclei, the thing that one of the ones that disappeared that was seen early in the spring, I guess, last year. In fact, that disappeared even before July of last year, I believe. Yeah. So that was, that must have been a really small one.
No reports of that. I wouldn't be surprised if we look back in our data and find it.
David Miller, U.S. News and World Report. Do we know the size of the diameter of the so-called fireball from the impact of G?
Yeah, I think we do have a pretty good measure. We saw G well enough, and actually one could compare it with the whole series of images that we saw on the limb from A and from E, that the initial fireball would probably grow to a diameter of about 8,000 kilometers before it starts to collapse. And then as it flattens back out again, it easily gets about twice as big. Does that answer the question?
Okay, we're coming back to Goddard now. Mark?
This is Mark Crow of the Houston Chronicle. Could you go over again about when M hit and who saw it, who reported it, who gets credit for that, and how does that change the total of known impacts that you think will happen? And is it possible that there are some other fragments that have turned off and on and that may have hit, and will you go back somehow and try to figure that out?
Okay. Yeah, the reports of observations of fragment M were made by Imke de Peter at the Keck telescope on Mauna Kea. And when she saw it, she wasn't sure if, she observed a flash, but she wasn't sure what was going on. I mean, so she even didn't say anything about it for a day. But then I talked to her on the phone, and our interactions convinced her that she was probably detecting it. Now it's going to take us time. I mean, this is the type of thing that's going to make us go back and look in our data for other small signals or relatively small signals in this case, and do some quantitative calculations. And I think it's possible we'll find more of these. Now, I'm not sure if I answered your question.
Yeah, sorry, I just wondered how this changed the fragment count
now for the whole whole train.
The fragment count. Well,
Yeah, is it
boy, I'm so
20?
confused that counting's getting difficult. I mean, I would say, okay, we're saying they're 21, and so that, boy, I don't even know if M was included in our 21 count. That's too tough a question.
M and J were parts of the original count of 21 as designated from the Mauna Kea observations by David Jewett and Jane Liu. Since that time, M and J had disappeared, but more fragments had formed. So Q split into 2 fragments, P split into 2 fragments. Meantime, P2 disappeared, or it became a puff. In addition, there was a fragment that split off of G,
a very small piece.
and rather more recently.
This reminds me of the games my dad used to play with me at dinner time and doing sequence of arithmetic.
Now
So where are we?
Now, if there's something left from all of these splittings, then we've got a total count that's greater than 21. Possibly, I can think of at least 4 more, or 3 more that you would add to that count. Now, whether they're all still there, that comes out of the issue. Is there something left when that thing disappears? But you talk about 24 that we might hope to see.
Yeah, and also just don't turn off the set quite yet after tomorrow. The trailing wing is going to continue to impact Jupiter. These are small particles.
That's a wing of dust, mostly?
It's mostly a wing of dust, really tiny particles, dust, sand grain size, maybe even smaller.
But we don't know what the real sources of the dust were. Maybe they're boulders.
Yes, they may be larger, but the interesting thing is that the impact sites, as you can see from the site of V and W tomorrow, much closer to the limb of Jupiter, to the edge, these trailing wing particles are actually going to be impacting on the visible side, the side we see. There are groups of astronomers, me included, that will be observing them very closely, especially for the next few weeks. They're expected to be most common, the most active between the end of the impacts tomorrow and the end of September, I think. And they're going to be progressively moving on to the side that we see. So the number of fragments, if you count all these little guys coming in, could go up quite substantially.
We have time for one more here.
I have questions, Dr. Weaver. I'd like to ask about the remaining or the build-up dust. Will it cause the meteor shower, every year to Jupiter, or will it tighten the Jupiter's ring, or what happened to the fall dust?
Yeah, there is a substantial amount of dust that actually misses Jupiter. It stays in orbit around Jupiter. Gene, I'll have to defer to you as to what's the ultimate fate of that dust.
Well, there's an astrophysicist at the University of Colorado Boulder by the name of Horanyi, who's done a very careful study of what happens to the dust that's in the tail, which will, all the collective tails, which will stay in orbit around Jupiter. And his analysis indicates when you take account of all the forces acting on these particles, which includes magnetic forces, because these will become charged, as well as the more conventional forces that we're used to thinking of. I don't want to give all the names. They're Poynting-Robertson effect, and there's direct solar radiation pressure, and so on. His analysis indicates that this dust will gradually settle down into more or less circular orbits and form a very diffuse kind of tall ring outside of the present ring of Jupiter. Now, whether there'll be enough dust there for anyone to see anything, that's another question. But at least that's where it's predicted to go.
Okay, we're going to have to stop at that for right now. I have time to remind you again about the briefing changes tomorrow at 2 p.m. and Saturday at 11 a.m. Eastern Time. We will clean feed the video, and if I could also ask for just a moment here and introduce from NASA headquarters the NASA Chief Scientist, Dr. France Cordova.
Thank you. On behalf of the NASA Administrator, I'd like to congratulate all the participants in this event for the inspiration that they continue to give and for the hard work and dedication. Who of us can ever forget the faces of the young observers as they saw the data come across this computer screen for the first time? I know I'm not going to forget the face of Heidi Hamill and my own intense suspense as I saw Roger yell, keeping us back from finding out exactly what was that element in the ultraviolet spectrum of the G impact site. Astronomy is about transforming images, those images that turn upside down our world view and that give us a new perspective on ourselves and on nature. What we see here this week is the culmination of nearly a year of intense preparation. Our goal of providing information and data in a timely fashion is being accomplished. And with the continued participation of these various individuals, we will continue to bring news of this comet through Saturday. I understand there's 5 pieces of the comet left to go. And in the next few months, we'll be observing the after effects of the comet's impacts, expecting to gain new and unprecedented insight into the origin and evolution of the solar system. I thank in particular Eugene and Carolyn Shoemaker and David Levy, the discoverers of the comet, for their efforts over the last week to discuss not only the unique scientific values of these impacts, but to express the excitement of science. They're an inspiration to all of us. And I thank the young observer scientists because they touch the future, uplifting the imaginations and fueling the aspirations of young people all around the world. The observations of this comet constitute one of the best examples of intercooperation between agencies also, and we have a very fruitful collaboration with the National Science Foundation and NASA in supporting many of these observations. Most professional observatories, as you've heard, around the world are observing the comet, and in addition, observers all over the world are using the computer electronic bulletin board maintained at the University of Maryland that Lucy McFadden has so eloquently spoken to this week. Networking specialists and computer experts around the world are playing an important role in making this data easily available and very quickly, too, to interested people everywhere. Ground crews I'd like to thank for the spacecraft like the Hubble, Galileo, Ulysses, the International Ultraviolet Explorer, Voyager, and the Extreme Ultraviolet Explorer, and the Kuiper Airborne Observatory, because they've been preparing for these observations for many months. We anticipate their results with a great sense of expectation. And finally, I'd like to thank the staffs of the Goddard Space Flight Center and the Space Telescope Science Institute for taking the lead and pulling together in one place all the right people to make sure what's happening is available to the broader public and the professional staffs of these organizations. On behalf of Mr. Golden, I commend them and their colleagues around the world for their highly successful efforts. And on behalf of myself, who am an astronomer, I thank you all for your affirmation that science is fun, if not quite as simple as ABG.
We'll see everyone again tomorrow morning and tomorrow afternoon at 2, and again Saturday at 11, and we'll have the clean feed coming on now for here and down the line. Thank you.
Today, we were pleasantly surprised to pick up event L, which was originally not expected to be captured because of the timing relative to the predictions of impact, but the actual impact occurred later, and we picked it up. And this one is actually brighter than H by almost a factor of 2. It's more like 5 to 6% the brightness of Jupiter, and it takes 35 seconds or so for the light to die back down again. So we think that we are seeing the actual meteor flash, the transition of the fragment through the atmosphere and the very hot emission from that, but over a very small streak of light across Jupiter. And this is of short duration and precedes the plumes and the fireballs that are being seen from other observatories.
It appears that the Io Taurus has not really changed that much yet, which may or may not be a surprise since it'll take a little while for this stuff to reach the Taurus. But one thing we have seen is that if we look at Jupiter alone in the extreme ultraviolet, we actually see signs of helium emission during the impacts that we don't see before. The plumes did go up fairly high because we have to have thrown helium far up in the atmosphere to be able to see this, several hundred kilometers, in order to see this emission through all the hydrogen that absorbs at these wavelengths.
Detecting a plume from the impact of our, this is using methane filter, 8,900 angstroms. We're somewhat surprised at being able to see it at all, because I don't recall there being that many detections of plumes in the visible. Most of them have been in the infrared so far. It may mean that it was a bigger piece than some people have been anticipating.